What are the key components of a relative criticality analysis? First, to simplify the process, the ranking compares systems of assets, which for the Gresham yielded a comparison of criticality between just 97 systems instead of 823 assets. Second, the systems are ranked against other systems within the plant. This is preferable to comparing criticality ranking against some external benchmarks, because ultimately the decisions are where to spend today's limited dollars and manpower to achieve maximum benefit for the set of assets under your management. Third, the relative criticality ranking rolls down to all the assets in the system, pending a further investigation such as reliability-centered maintenance or RCM. This sets priorities for day-to-day maintenance work. Finally, relative criticality is another strategy of ranking by consequence and likelihood of failure in much the same way that a classical risk matrix does. As mentioned, the analysis of relative criticality is best performed on a system of assets that usually work together to perform a certain function. Systems thinking, or perspective, is a very different approach compared to viewing assets as individual units. However, for many applications, particularly where downtime cannot be tolerated, there are two pumps that work together to provide continuous flow of product even if one pump stops working. So, stepping back and thinking of the design function for the group rather than the individual pump, the system is a much better unit for analysis. The other key concept is 100% coverage, which must go hand in hand with the system's thinking to provide groupings where 100% of the assets can be allocated. To visualize the concept of systems with 100% coverage, imagine that you draw a line around a group of assets that you manage. This might be your manufacturing facility or wastewater plant, which has a fence line that is easy to identify. Or maybe you're responsible for a city and must manage roads, sidewalks, parks, and the fence line is a little bit more difficult to visualize. Either way, the key is to recognize that at the highest level there is a definition of all or 100% of the assets you're responsible for, and on that slide we call this the facility. Next, we divide the facility into the natural groupings that you might normally review on. For Gresham, the plant is monitored by unit process, which included the headworks, where the wastewater flows from the plant, the biological treatment process, and the sludge handling, for example. Each compares with a process that is monitored for performance effectiveness in order to achieve the ultimate goal of clean water. Again, keeping in mind that this grouping process, you are dividing up 100% of the assets into groups. The unit process breaks down further into systems of assets. As an example of a system that includes 100% of the assets within it, let us consider this network diagram of a group of assets. If we were only looking to identify or count assets, we might just list that we have 2 tanks and 3 pumps. However, we can draw a boundary around this grouping, and because they work together to provide a function of store and transfer sludge. Now when we ask the question, what is necessary to store and transfer sludge, as a function we recognize that we need tanks, pumps, valves, and pipes. And using the concept of group assets, we can quickly describe all of the pipe within the system as a group asset. The really key point is that now, recognizing a group of assets as a system, which has a function, we can now ask the question, how can this system fail to provide its function? And further, how will that failure rank in criticality relative to other systems of assets that I currently manage? The system hierarchy also makes it easy to review your asset listing to make sure that you now have included all the assets in a particular system. This slide shows an example of a typical wastewater collection system pump station and how it breaks down into a set of key systems, which includes the building and grounds, electrical, and pumping systems. To summarize the keys to developing a system hierarchy, remember that each asset provides at least one purpose for being in the system, but most assets do not provide a system function all on their own. Systems thinking is important for your overall asset management program because it will allow you to evaluate the cost of providing a function or level of service on the smallest grouping of assets possible. As your asset management program begins to expand, you may want to use reliability-centered maintenance, or RCM, to optimize the lifecycle costs. RCM is also conducted on a system level. But for this example, the systems thinking is also the quickest hierarchy level to conduct the relative criticality analysis.